For 60 years, when we imagine humans living beyond Earth, one world dominates the picture: Mars. The red planet has become so closely tied to the idea of settlement that we rarely stop to ask a more basic question. Is Mars actually the best place for us to go? Because reaching another world and being able to live there are not the same problem. Mars is close enough to tempt us, familiar enough to feel achievable, and difficult in ways we have spent decades trying to solve. But some of its deepest problems may not disappear simply because our technology improves. And there's another world that changes the comparison entirely. Titan, Saturn's largest moon, a place wrapped in a thick atmosphere, with surface pressure surprisingly close to Earth's, and a set of dangers almost completely different from those waiting on Mars. By the end of tonight, you're going to understand why Mars became humanity's obvious destination, which of its problems may prove hardest to overcome, and why Titan's cold and enormous distance may be more solvable than they first appear. Before we get started, take a second to like and subscribe. It really helps the channel. Now, let's begin. Long before anyone imagined rockets or colonies, Mars had already captured human attention. 3,000 years ago, Babylonian astronomers were tracking a red light moving across the night sky and pressing its path into wet clay with reed styluses. Across generation after generation, that wandering point kept demanding explanation. Ancient cultures noticed it for simple reasons. It was bright. It moved strangely against the fixed stars. And unlike worlds that could not be seen without modern instruments, Mars announced itself every clear night. The Egyptians called it the Red One. The Greeks associated it with their god of war. The Romans kept the name Mars, and that name outlasted both empires. At that stage, nobody knew whether Mars was remotely suitable for life. They did not know its atmospheric pressure, its temperature, or even what its surface really looked like. They simply knew it was there. That visibility gave Mars an enormous head start in the human imagination. We watched it for thousands of years before we understood it, and every improvement in astronomy seemed to pull the planet a little closer. In 1610, Galileo turned a crude, refracting telescope toward Mars and saw something no one had seen before. Not a point of light, a disk, a physical world, with edges, with size, with a surface waiting to be measured. Over the next 2 centuries, the telescopes kept improving, and the resemblance to Earth kept growing with them. Astronomers watched surface markings shift with the seasons. They clocked the Martian day at roughly 24 hours and 37 minutes, only about 22 minutes longer than a day on Earth, close enough that an observer could imagine stepping outside into something like a familiar morning. They saw polar caps swell through the Martian winter and shrink through the Martian summer, mimicking the ice sheets of home. Of every world visible from Earth, Mars looked the most familiar, a colder, drier version of home, and that resemblance did more work than any argument could have. But here's where it gets strange. In 1877, the Italian astronomer Giovanni Schiaparelli mapped a network of faint linear features on the Martian surface and called them canali, simply the Italian word for channels. English speakers translate the word as canals, and canals do not occur in nature. Canals are built by someone for a reason. That single mistranslation became one of the most consequential errors in the history of science. Percival Lowell took it from there. A wealthy American businessman with an amateur's telescope and a believer's certainty, he built his own observatory in Flagstaff, Arizona, mapped an increasingly intricate grid of straight lines across the planet, and published 3 books arguing that an advanced, dying civilization had engineered a planet-wide irrigation system, moving water from the melting poles to thirsty equatorial deserts. It was elegant, it was emotionally irresistible, and it was completely wrong. Mars is the obvious next step for a species already reaching for the planets. The reasoning would eventually run. Not because anyone had measured that, because one man's beautiful mistake never stopped echoing through the decades that followed. In 1898, everything changed again, this time in fiction rather than in any observatory. H.G. Wells published The War of the Worlds, and Mars stopped being just a red disk with rumoured canals. It became Earth's twin, Earth's rival, and eventually Earth's backup plan. The branding never faded after that. It only evolved. Wells's Invading Martians became Kim Stanley Robinson's terraforming dreams decades later. Those dreams became corporate colonization pitches. Those pitches became the slide decks of billionaire rocket engineers, each one assuming the same destination as the last, never quite pausing to ask why. The line from one mistranslated word to a modern launch manifest runs unbroken. And here is the part almost no one remembers. By the early 20th century, better telescopes looked again, closer and clearer than Schiaparelli or Lowell ever had. And the canals were gone. They had never been there. They were an illusion, faint random markings stitched into straight lines by a brain built to find patterns whether or not the patterns are real. Not a network of canals, not a dying civilization rationing its last water across a red desert. A trick of human eyesight, and nothing more. So, which was it? A world engineered by a fading intelligence, or a world imagined into that shape by ours? By the time anyone could answer that question with certainty, it no longer mattered. Mars had already won. It carried a 2,000-year head start on every other planet in the solar system. A head start built on watching, on waiting, on wanting, and for a while on believing in something that was never real to begin with. No other world carried that kind of mythology. No other world had already been cast, centuries in advance, as humanity's next home. The mythology had won before the science ever got a vote. It settled into museums, into classrooms, into the assumptions of engineers who had not yet been born when Lowell built his observatory. And when the rockets were finally ready to fly, nobody had to stop and ask where to point them. The decision had already been made, quietly, over 2,000 years, by nothing more scientific than familiarity. That quiet, centuries-old decision was still cashing itself in when the space race finally began in the late 1950s. Neither superpower sat down and compared destinations. Nobody weighed Mars against Venus, against the Moon, against anywhere else worth the fuel and the risk. Mars was simply where you went next, because the story already existed. And the only real question left standing was who would get there first. The Soviet Union answered that question in 1962, launching Mars 1, the first spacecraft ever aimed deliberately at another planet. Somewhere in the long, empty stretch between the two worlds, it lost contact with the ground and was never heard from again. No one ever learned exactly what killed it. That silence set the tone for the decade that followed. Mission after mission went out, from both nations, funded on hope and pointed at the same red target, and most of them crashed on launch, drifted off course, lost their signal mid-flight, or missed the planet entirely. The early failure rate climbed past 70%. Mars earned a nickname for it, and the nickname stuck. The graveyard of spacecraft. Close enough to attempt, far enough away to punish every shortcut. Both nations kept trying anyway, pouring money and prestige into launch after launch, watching signal after signal go silent over the same stretch of years, because turning back was never seriously on the table. Then, in 1965, one finally made it through. NASA's Mariner 4 passed within roughly 10,000 kilometers of the surface and sent home 22 photographs. Grainy, black and white, and nothing like what 2 centuries of hopeful astronomers had trained themselves to expect. No canals, no vegetation, no fading civilization rationing its last water across a dying desert. Just craters, and more craters, layered over craters older still, and an atmosphere far thinner than anyone had dared to guess. Mars looked less like a twin of Earth, and more like Earth's own moon, dropped into a slightly different orbit. The romantic vision was gone in 22 photographs. That should have been the end of the story. A dead, cratered rock rarely holds anyone's attention for long. That is when the pattern broke. Instead of losing interest, the scientific community leaned in harder. A dead world is a disappointment. A dead world that used to be something else entirely is a mystery. And mysteries, unlike disappointments, are what keep budgets alive. If Mars was once warmer, once wetter, where did all that water actually go? If life had ever taken hold there, even briefly, could any trace of it still survive underground, or frozen solid, or sealed inside ancient rock? Every disappointing answer only generated 10 new questions behind it. Mars had failed as humanity's twin. It succeeded instead as a laboratory, and a laboratory attracts funding in a way a dead rock never can. 6 years later, in 1971, Mariner 9 became the first spacecraft ever to orbit another planet. And what it found rewrote the picture all over again. Not flat, not lifeless looking, scarred instead by a violent, dramatic past written straight across its surface. Olympus Mons rose into view first, a shield volcano roughly 22 kilometers tall, dwarfing anything Earth has ever built through fire from below. Valles Marineris opened beneath it, a canyon system stretching more than 4,000 kilometers, long enough to swallow the Grand Canyon whole, without even noticing it was there. And running through the older terrain, channels and valley networks that looked unmistakably carved by flowing liquid, water most likely, sometime in a past that predates almost everything else in the solar system by billions of years. Mars had a history now, and a world with a history is a world worth continuing to fund. That momentum carried straight into 1976, when NASA landed 2 spacecraft on the surface within weeks of each other. Viking 1 and Viking 2 sent back the first color panoramas ever taken from the ground of another planet, a rocky desert stretched out beneath a dusty, butterscotch sky. Each lander carried 3 separate biology experiments, built for exactly one purpose: find out, once and for all, whether anything alive was living in that soil. The results refused to cooperate. One experiment, the labeled release test, returned a positive signal, the kind of result that would normally mean life. The other 2 came back negative, or too ambiguous to call either way. Most scientists eventually sided with a sterile Mars, but the debate never actually closed. A single unresolved positive sitting against 2 negatives is not proof of nothing. It is a maybe. And a maybe, it turned out, is one of the most durable engines of scientific interest there is. Some researchers still argue about that one signal today, decades later, no closer to a final answer than they were in 1976. Viking cost close to $1 billion in 1976 currency, more than $5 billion in today's money. By any engineering measure, it was a triumph. But it did not deliver the one thing that keeps political enthusiasm burning for decades. A clean, transformative discovery the whole world could point to. No confirmed life, no definitive death sentence either. Just an open question, expensive and unresolved, left sitting on the table. After that, Mars went quiet. Nearly 2 decades passed with no new landers, shrinking budgets, and NASA's attention pulled elsewhere, toward the space shuttle and the demands of low Earth orbit. No missions launched toward the red planet. No new pictures came back from its surface. Mars simply waited, its unanswered questions sitting exactly where Viking had left them, until something changed enough for anyone to look again. The wait ended in the mid-1990s. When Mars came back, it came back cheaper, and this time the whole world was watching. NASA Administrator Daniel Goldin drove the revival under a new philosophy: faster, better, cheaper, a deliberate break from the billion-dollar model that had built Viking 2 decades earlier. Smaller missions, shorter timelines, and a willingness to accept more risk in exchange for far less money spent per launch. On July 4th, 1997, Mars Pathfinder landed and released Sojourner, a rover roughly the size of a microwave oven, built and flown for a fraction of what its predecessor had cost. On paper, it looked like a modest mission, a small machine rolling a short distance across a dusty plain. It became something else entirely. Images of that small robot picking its way around rocks spread across the newly public internet faster than any planetary mission had ever traveled before. People everywhere watched a wheeled machine cross another world in something close to real time, on their own screens, at their own kitchen tables. The emotional connection that had gone quiet for 2 decades came back, and it came back fast. From that point on, Mars never left the stage again. Spirit and Opportunity touched down in 2004, each one engineered to survive 90 days on the surface before its instruments were expected to fail. 90 days came and went. Opportunity kept moving for nearly 15 years, dragging its wheels across more than 45 kilometers of Martian ground, farther than a full marathon, covered 1 careful meter at a time by a machine no one had built to outlive its own warranty. Curiosity followed in 2012, lowered onto the surface by a sky crane landing system unlike anything flown before, a rocket-powered stage hovering just above the ground to set a laboratory the size of a small car gently onto the dust. It carried the most capable science instrument package ever sent to another world. Perseverance arrived in 2021 with Ingenuity riding along for the descent, and Ingenuity became the first powered aircraft ever to fly under its own power on another planet. A few grams of spinning blades succeeding where nothing had ever left the ground before. 4 missions, 4 generations of hardware, each one more capable than the last. But not one of them was built to ask whether Mars was the right choice at all. Every one of them was built to answer smaller questions about a choice already made, long before any of them launched. Together, these missions changed what was actually known about Mars, not what was hoped about it. Liquid water once moved across that surface in real quantity, carving channels that still show in the rock today. Organic molecules, the carbon-based building blocks life depends on, turned up inside Martian samples. The geological record showed a planet as varied and violent in its history as Earth's own. And in certain places, briefly, billions of years ago, the conditions needed for microbial life may have existed. Not confirmed life, only the conditions that could have supported it. That distinction still holds, and no rover since has closed it. The rest of the world noticed, and followed. The European Space Agency put Mars Express into orbit in 2003. India's space agency reached Mars on its very first attempt in 2014, for a mission that cost less than the production budget of many Hollywood films. Proof that a nation did not need NASA's budget to join the club. China landed its Zhurong rover in 2021, becoming only the second nation in history to drive a rover across another planet's surface. The United Arab Emirates sent its Hope orbiter into Martian orbit that same year, a country with no prior planetary program at all. One agency after another, most of them with no history at Mars whatsoever, chose the exact same destination everyone before them had already chosen. None of them ran the comparison from scratch. None of them asked whether some other world, one nobody had visited yet, might actually serve their purposes better. Mars was simply where the tools, the trajectories, and the track record already pointed. By any measure, Mars became the most visited world in the solar system after Earth. It is worth pausing on why. Not because the science demanded Mars above every other candidate in the solar system, because the infrastructure already existed, because the expectation was already cemented, mission after mission, decade after decade, until turning toward anywhere else would have meant starting over from nothing. Because the orbital mechanics cooperated more than they did anywhere else worth going. Infrastructure existed. Expectation was fixed in place. The orbits lined up, again and again, on a predictable schedule. None of that is a verdict on which world actually deserves people. It is the path of least resistance, paved one mission at a time until, from the outside, it looked like the only road there had ever been. And underneath that convenience sits something the momentum alone cannot explain. A real number, not a habit, not an inherited assumption, an actual physical advantage that has earned the right to an honest hearing before anyone dares to question it. That advantage has a name, and it starts with distance. Mars orbits the Sun at an average of about 228 million kilometers from Earth. At its closest, when the two planets line up on the same side of the Sun in what astronomers call opposition, that gap shrinks to roughly 55 million kilometers. Drive that distance at highway speed, non-stop, day and night, and the trip would still take more than 60 years. Even the close pass is a genuine journey, but it is a journey the solar system offers on a schedule. Every 26 months, the two orbits line up well enough for what's called a Hohmann transfer, an orbital path shaped, so a spacecraft coasts most of the way on momentum instead of burning fuel to fight its trajectory the whole way there. Miss the window and the wait is 2 more years. The entire mission slipping down the calendar until the planets line up again. Catch it, and a spacecraft on ordinary chemical propulsion reaches Mars in 6 to 9 months, with a radio signal crossing the gap in 3 to 22 minutes, depending on where the planets sit that day. Large numbers by human standards. Manageable numbers by engineering standards. Getting there also costs a fuel budget, not just a distance. Engineers call it delta V, the total change in velocity a mission has to afford across every maneuver from launch to landing. Think of it less like a fuel tank and more like a household budget. One account that every burn withdraws from: launch, course correction, orbit insertion, landing, with nothing ever refilled along the way. Leaving a low Earth orbit for Mars spends about 3.6 kilometers per second of that budget, with more required for arrival and landing. A full round trip, insertion, landing, ascent, and the burn home again adds up to roughly 16 kilometers per second total. Every kilometer of it is achievable with rocket engines that already exist. Given a large enough vehicle, enough fuel carried or manufactured along the way, and careful staging of each burn. Nothing about the Mars number demands a technology that has not already flown. The budget is large, but it is a budget engineers already know how to balance. Now widen the view. Jupiter sits about 5.2 astronomical units from the Sun, over 5 times farther out than Earth. Saturn sits at 9.5 astronomical units, nearly 10 times Earth's distance, with its largest moon trailing along beside it, roughly 1.2 billion kilometers from home. Drive that distance at highway speed, and the trip would outlast 1,000 years before it finished. Reaching it by rocket costs a fuel budget so much steeper that no spacecraft has ever attempted the trip directly, carrying every drop of propellant it would need from the start. Every mission that has gone that far borrowed velocity instead, a maneuver called a gravity assist, swinging close past a planet's gravity well and stealing a sliver of its momentum on the way past. Trading years of extra flight time for fuel nobody had to carry, stretching the journey to 7 years or more. Cassini remains the only spacecraft ever to orbit Saturn. It launched in 1997 and stole momentum twice from Venus, once from Earth, and once from Jupiter, threading 4 separate flybys before it finally reached Saturn in 2004. 7 years of cruise just to arrive, and Cassini carried instruments, not people who needed to eat, breathe, and stay sane along the way. Wait. A crewed mission carrying people instead of instruments would need a steeper delta V budget still, and even the most optimistic reactors under study today, engines that heat propellant directly instead of burning it, put the one-way transit at 4 to 6 years. Not a season, not a year. Years, plural, before anyone sets foot on anything. And the moment a crew arrived, distance would keep charging interest. A radio signal between Earth and the Saturn system takes somewhere between 67 and 87 minutes each way. Ask a question, and the answer comes back nearly 3 hours later, roughly the time it takes to watch the same film twice before a single reply arrives. That is not an inconvenience to plan around. It is a different way of making every decision, one where nobody on the ground can talk a crew through an emergency as it happens, because by the time the words arrive, the emergency has already resolved itself one way or another, without them. Mission Control becomes an advisor writing letters, not a voice on the other end of the line. Even the calendar refuses to cooperate the way it does for Mars. Mars offers a launch window every 26 months, predictable enough to plan a decade of missions in advance. Reaching Saturn efficiently means waiting for several planets to fall into alignment at once for the gravity assist to work, a rarer and messier kind of coincidence that resists the same tidy scheduling. The pipeline to Mars runs on a regular, well-understood rhythm, the kind an agency can build a decade of budgets and staffing plans around. The pipeline to Saturn runs in fits and starts, complicated every single time, demanding a fresh trajectory design for nearly every attempt. So the case for Mars, on the numbers alone, is real, closer, cheaper in fuel, faster to reach, easier to talk to, open for business every 26 months, like clockwork. None of that is myth, and none of it is momentum dressed up as fact. It is arithmetic, and for 60 years of mission planners working the problem, the arithmetic has always checked out. But arithmetic only measures how easily a door opens. It says nothing about what is waiting on the other side of it. What waited on the other side of that door did not build itself in a single trip. It built itself in 60 years of trips, each one making the next trip a little more certain, until certainty stopped asking whether the door was the right one to walk through. Here is how the cycle actually worked. Mars was closer, so the first missions went there. So engineering heritage accumulated. Heritage accumulated, so later missions grew cheaper and more reliable. Missions succeeded, so knowledge grew. Knowledge grew, so future missions could be planned with precision instead of guesswork. Precise plans existed, so funders felt comfortable approving them. And funding flowed, so institutional momentum built, decade after decade, until Mars was no longer one candidate among several. It was effectively the only candidate anyone in mainstream space policy took seriously at all. Then, one person amplified that momentum beyond anything a government budget could manage. Elon Musk did not just fund a Mars program. He moved the idea out of science fiction and into corporate strategy, backed by hardware that actually flies. SpaceX announced the goal of a permanent, self-sustaining city on Mars, and built Starship to get there, the largest, most powerful rocket ever constructed. The stainless steel hull, the refueling concept, the payload volume, the landing profile, all of it optimized for one destination and no other. NASA's own program reinforces the same gravity. Artemis is framed as a return to the moon, but read the fine print, and the moon is not the point. The planned Gateway Station in lunar orbit exists to test deep space habitat systems Mars will eventually need. Every resource extraction test, every advanced life support upgrade, every congressional budget justification connects back to the same endgame. The moon is the rehearsal. Mars is the destination. And it is not only one country or one billionaire. China has announced crewed Mars missions targeting the late 2030s to early 2040s. Europe's space agency is partnering with NASA on a Mars sample return campaign. Russia keeps announcing Mars ambitions its budget cannot yet support. Japan and India keep developing the technology anyway. Every major spacefaring nation, without exception, treats Mars as the obvious next step beyond the moon. But here's where it gets strange. Universal agreement feels like proof. It isn't. Everyone converging on the same answer does not make the answer correct. It means a decision got made decades ago by people working with less information than we have now, for reasons that were practical rather than optimal, and nobody with the power to change course has ever seriously gone back and asked whether that decision still holds. Not confirmation. An echo, repeating for 60 years because nothing forced it to stop. So look at the case Mars actually makes for itself. The version in every brochure and every keynote. It sits in our cosmic front yard. Its day and night cycle nearly matches Earth's. Confirmed water ice waits at the poles and under the mid-latitude soil. Its carbon dioxide could, in theory, be processed into oxygen and rocket fuel. We have mapped its surface at resolutions fine enough to spot a parked car, and robotic wheels have covered more than 70 kilometers of it combined, farther than the distance between two neighboring towns, driven one cautious meter at a time by 5 separate machines. We know Mars better than any world besides our own. On paper, it reads like a closed case, but brochures are built to sell, not to inform. The version that gets printed leans on every similarity and buries every hazard. That atmosphere sitting in the pamphlet as a familiar blue haze is in fact 95% carbon dioxide, at under 1% of the pressure your body evolved to expect. That gentle day and night cycle carries temperature swings of nearly 80 degrees between the same afternoon and the following midnight. The water ice sits buried under meters of soil, laced with a toxic compound no brochure mentions. And the radiation reaching that surface has no equivalent anywhere on Earth, outside a nuclear accident's fenced exclusion zone. Not a minor omission. A structural one. Not a detail the next generation of engineers can design around. A set of physical facts the brochure simply left off the page. Which brings the whole argument to its real hinge. Mars became the default because it was the first plausible option, the nearest world that looked survivable enough and reachable with rockets we already knew how to build. Every decision after that first one stacked on top of it, until the original choice disappeared from view entirely. Nobody questions the foundation of a building they're already living in, but nearest and best have never been the same word. Reaching a world first is not the same as thriving there for 1,000 years. Planting a flag is not the same as sustaining a civilization. And the physical constraints waiting on Mars do not care how much momentum brought us there. How many rockets were built? How many nations signed on? Radiation that rewrites DNA does not negotiate with funding cycles. Pressure that boils exposed blood does not care about institutional consensus. Soil that poisons the thyroid, gravity that may be too weak for a body to grow properly in, none of it reads a roadmap. Every habitat concept drafted so far assumes these problems are solvable. Some of them probably are. Some of them may not be. Not in decades, not in centuries, possibly not ever, not within what Mars itself allows. That is the actual question this argument has been circling since the beginning. Not which world we can reach. Which world lets us stay? Staying begins with air, or more precisely, with its almost total absence. Step onto the Martian surface without a pressure suit, and death arrives in about 15 seconds, roughly the time it takes to read this sentence aloud twice. Not from cold. Average surface temperature hovers near minus 60 degrees Celsius, close to what the frozen interior of Antarctica endures through its darkest winter months, and cold alone does not kill a body in 15 seconds. Not from the carbon dioxide either, unbreathable as it is, but not fast enough to explain what actually happens. The actual killer is quieter than either one, pressure or what little remains of it. It has dropped so low that the moisture inside a human body has nowhere left to stay liquid. Your saliva boils, your eyes boil, your lungs boil, not from heat, because the air pressing back from outside has grown too thin to hold anything down, So the fluid inside your body pushes outward against nothing at all, and biology tears itself apart from within, simply because Mars cannot supply enough air to keep liquid stable at the temperature of a living cell. Here is the number behind that failure. Mars averages around 600 pascals of surface pressure. Earth, at sea level, sits at 101.1325. That leaves Mars with less than 1% of what a human body evolved to expect. Roughly the pressure found 35 kilometers above Earth's surface, deep in the stratosphere, well above where any commercial jet has ever cruised. Felix Baumgartner needed a fully pressurized, near space-rated suit just to survive a jump from 39 kilometers. And even then, only for a few falling minutes before a parachute and thicker air caught him. On Mars, that same near vacuum sits at ground level, permanently, everywhere a boot could ever land. There is no low point on the planet where the air thickens back into something forgiving. Surely somewhere on the planet offers relief, a canyon deep enough, a basin low enough, to trap a little more air against the ground. The way pressure thickens at the bottom of a valley on Earth, Valles Marineris drops nearly 7 kilometers below the surrounding plateau, a deeper cut than anything carved into Earth, a gash long enough to swallow entire mountain ranges. At its floor, pressure climbs to perhaps 1200 pascals, twice the surface average elsewhere on the planet, still barely 1% of Earth's, still lethal. There is no elevation low enough anywhere on Mars to fix this. Floor to summit, the whole planet is a pressure desert, and the deepest canyon it has to offer only proves the point. This is the hazard nearly everything else grows out of, because a real atmosphere does more than let a body breathe. It performs a set of free, invisible services nobody on Earth ever has to think about, let alone pay for. It absorbs most incoming ultraviolet light before it reaches skin. It burns up incoming debris through friction before it ever reaches ground. It holds enough heat to soften the transition between day and night. And it stays dense enough, everywhere, to keep liquid water from simply evaporating away into nothing. Mars offers none of it. Ultraviolet light reaches the ground almost unfiltered, the way it would at the summit of a mountain far taller than any that exists on Earth. Debris that would burn to ash streaking through Earth's sky instead reaches the Martian surface with barely any deceleration at all, arriving as a hazard rather than a spark of light in the night. That 80-degree swing between one afternoon and the following midnight, already described, exists precisely because the air is too thin to buffer it, and water, wherever it survives as ice, cannot melt and pool the way it does at home. Mars sits at or below the exact pressure liquid water needs to exist at all. Ice there does not melt. It sublimates, jumping straight from solid to gas, skipping the liquid stage entirely. Leave a cup of water exposed to the Martian air, and it would flash into vapor before it ever reached your mouth, gone before the thought of drinking it had finished forming. So every structure has to do, permanently and without pause, what the atmosphere provides for free across the whole of Earth. Every habitat, every greenhouse, every corridor connecting one building to the next has to hold an internal atmosphere nearly 170 times denser than the air pressing in from outside. Every wall becomes a dam holding back vacuum. At every window is a weak point built into that dam. Every airlock is a controlled failure allowed on purpose, the one place the dam is permitted to open, briefly, on command. Engineers already know how to build pressure vessels. Submarines hold back an ocean. Aircraft cabins hold in breathable air at altitude, over and over, flight after flight. The methods are decades old and well understood, but submarines return to port. Aircraft fuselages are inspected after every flight, and retired once the metal fatigue accumulates past a known limit. Somewhere in the tens of thousands of pressurization cycles, a threshold most planes only reach after 30 years of routine, daily service with a full maintenance crew, and a supply chain of replacement parts waiting on the ground. Even the International Space Station, circling in continuous orbit for more than 2 decades, still needs constant seal checks, leak detection, and patching after every micrometeorite strike, and every one of those repairs is supported by cargo launched from Earth. No pressure vessel in human history has ever been asked to run without interruption, without a port to return to, for generations, with no replacement parts shipped from anywhere at all. And the failure mode underneath all of it is not gradual. On Earth, a crack in a wall lets in a draft, an inconvenience and nothing more, patched at leisure over a weekend. On Mars, that same crack lets in death, and it arrives in the same 15 seconds already described, with no graceful in-between state for anyone to react inside of. There is no partial failure available, sealed or breached, alive or not. Pressure was only the first door the vacuum opened. What comes through next reaches every unshielded body on the surface, and no wall built so far can fully close against it. The vacuum stops at a wall. This next threat does not. Earth survives its position in space because it wears 2 shields at once. A magnetosphere, generated by the churn of liquid iron thousands of kilometers below the surface, bends most of the sun's charged particles away and funnels them toward the poles, where they paint the sky in aurora rather than striking the ground you stand on. Above that, a thick atmosphere absorbs nearly everything the magnetic field lets through, including the harshest ultraviolet and X-ray light. Neither shield alone would be enough. Together, one deflecting and one absorbing, they hold Earth's surface dose to about 2.5 millisieverts a year. Millisieverts being the standard unit for radiation absorbed by the body, so small it barely registers. A quiet background hum nobody bothers to track. You live your whole life underneath both shields at once, and never once have to think about either. Mars had that same protection once. It lost it. About 4 billion years ago, the planet's iron core cooled and partly solidified, and the dynamo driving its magnetic field shut down. No spinning liquid core left to generate a field means no field, and no field means nothing left to deflect. Without a magnetosphere to hold it back, the solar wind began peeling the atmosphere away, molecule by molecule, and it has never stopped. The MAVEN orbiter, launched specifically to watch this erosion from above since 2014, measured the ongoing loss directly. About 100 grams of gas, stripped away every second, small on its own, multiplied across 3.5 billion years, it adds up to an entire ocean of atmosphere, gone, and the thin remnants still clinging to the surface today keeps shrinking by the same slow measure. What's left is thin enough to let radiation through almost unfiltered. Curiosity's onboard detector, built to measure exactly this, records a baseline surface dose of about 233 millisieverts a year, roughly 2/3 of a millisievert every day. That is nearly 100 times what Earth absorbs in the same 12 months. Constant, unfiltered, a drizzle of high-energy particles raining down from supernova remnants and violent galaxies across the Milky Way, every hour of every day. And that is only the baseline, the steady drizzle falling every hour regardless of what the sun is doing. The sun adds spikes on top of it. A moderate flare in 2017, observed directly by Curiosity, roughly doubled the surface dose for several hours before fading back down. The larger events, several of which arrive every solar cycle, can deliver hundreds of millisieverts in a single day. An entire year's baseline dose compressed into an afternoon. NASA sets a career radiation limit of 600 millisieverts for its astronauts, accumulated across every mission an astronaut ever flies. One severe storm could approach that limit by itself in a single afternoon on a world with no magnetosphere to soften the blow. Warning time between detection and impact can run as short as 15 to 30 minutes, barely enough to reach shelter, let alone build one. Shielding should solve this. Wait, it can make things worse. Galactic cosmic rays are not ordinary radiation. They are protons and heavier atomic nuclei moving at extraordinary energy, carrying billions of electron volts, the unit physicists use to measure how much punch a single particle carries. At that energy, they punch straight through several meters of aluminum, rock, or packed ground before losing momentum. And when they finally strike something solid, they do not simply stop there. They shatter the atoms they hit, scattering a spray of secondary neutrons and gamma rays outward from the point of impact. A cascade that can do more biological damage to living tissue than the original particle ever would have on its own. Thin shielding does not block a cosmic ray. It turns one dangerous particle into several. Only serious mass helps, several meters of it, dense and continuous. Proposals exist to bury habitats under 3 meters of regolith, the loose broken rock and dust that covers the Martian surface, roughly the height of a single room stacked overhead. Even that is not fully sufficient. 2 meters reduces the flux without eliminating it, and building, sealing, and maintaining a permanently buried settlement adds an entirely separate engineering burden of its own. Time changes the arithmetic completely. A short mission, 12 to 18 months on the surface, carries an elevated but survivable dose, comparable to an extended stay aboard the International Space Station, a risk an informed astronaut might reasonably choose to accept. Permanent settlement does not survive the same math. 30 years, 7,000 millisieverts, unshielded, more than 11 times NASA's career limit, absorbed in one ordinary lifetime, not a career. Even 2 meters of buried regolith does not bring that number down to anything an occupational safety standard on Earth would permit. Chronic exposure at these levels carries its own list. Elevated cancer risk, accelerated cardiovascular disease, the kind of wear normally seen decades later in life, arriving early, cataracts, emerging evidence of cognitive decline from cumulative damage to the nervous system itself. None of this is speculation about some hypothetical dose. It is the documented cost of numbers already measured on the Martian surface today. Animal studies at the Brookhaven National Laboratory, simulating galactic cosmic rays in rodents at doses matched to a multi-year Mars stay, found measurable impairment to learning, memory, and executive function. Whether that maps cleanly onto humans is still debated, but no better evidence exists, because no human has ever accumulated a Mars-equivalent dose to study, and none ever safely could. The most troubling unknown sits 1 generation further out. A developing embryo divides its cells rapidly, far faster than adult tissue ever does, and every one of those divisions is another chance for a radiation-induced error to propagate outward into the organs and systems still forming. Get the error early enough, and it does not stay small. No data exists on human reproduction at Mars surface radiation levels. None can exist. No ethical framework permits the experiment that would produce it. No review board on Earth would approve testing chronic radiation exposure on human pregnancy. Not a risk you disclose, and let someone choose to accept. A risk no institution on Earth would ever be allowed to test in the first place. Any settlement built to last across generations is, by definition, running that experiment anyway, on every child born there, without consent and without a single prior data point to work from. The sky was only the second door. The ground still has one more waiting. The sky was the second door. The ground is the third, and it does not need to be crossed to reach you. It is already underfoot, every day, in every handful of dust, a boot kicks loose. Below the radiation, the soil itself turns out to be a chemical hazard, and there is no clean fix waiting for it. Martian regolith is laced with perchlorate salts, compounds built from chlorine and oxygen, first detected by the Phoenix lander in 2008, and confirmed at site after site by Curiosity since. The concentration runs from about 0.5% to a full percent by weight, sometimes higher depending on the region sampled, roughly a heaping spoonful of the compound sitting in every few cups of ordinary Martian dirt. That sounds small. It is not. On Earth, perchlorate is a regulated contaminant, not a soil additive. It interferes with the thyroid by blocking the gland's uptake of iodine, disrupting the hormones that govern metabolism, growth, and a developing nervous system. The US EPA sets a safe reference dose at 0.7 of a microgram per kilogram of body weight per day, a quantity so small it is closer to a single grain of salt dissolved across a swimming pool than anything a kitchen scale could register. Martian soil holds perchlorate at concentrations millions of times above that line, not a hazard you manage carefully with gloves and a filter, a hazard you stay away from entirely. So why not simply wash the ground clean and farm it anyway? Growing anything in that soil first means getting the perchlorate out, and the straightforward method is repeated washing, flushing the salts loose with water until the soil runs clear. But every litre of that water has to be mined from subsurface ice, melted and purified before it ever touches a shovel of dirt, and each kilogram of treated soil can demand several litres of it. Water already budgeted for drinking, for breathing, for keeping a sealed habitat alive at all. What comes off the soil afterward is itself perchlorate-laden wastewater. One more substance that has to be treated or disposed of. One more link in a chain already stretched thin. A biological shortcut exists. Certain bacteria metabolize perchlorate directly, breaking it down into ordinary chloride and oxygen. But keeping that culture alive and uncontaminated inside a sealed greenhouse for years, for decades, is a second fragile system built on top of a first one. Most designs give up on the ground rather than fight it. Food gets grown hydroponically instead, roots suspended in nutrient solution inside sterilized water, no regolith involved anywhere in the process, no washing, no bacterial cultures, no wastewater to treat, and that is where the reveal lands. Landing on a solid planet was supposed to mean farming the ground beneath your own boots. It does not. If the crop never touches native soil, the facility growing it could sit in orbit. It could sit on any other airless rock in the solar system. Nothing about the harvest would change. The surface itself adds nothing. The soil is not a resource anymore. It is a contaminant, something to be kept out, filtered from the air, washed from every surface it settles on. And it does not stay content sitting on the ground. Martian dust is extraordinarily fine, particles averaging only about 3 micrometers across, thinner than a single strand of spider silk, small enough to slip past the body's normal defenses and settle deep in the lungs, where nothing clears it back out. It also carries an electric charge, built up by ultraviolet light and by friction with everything it brushes against. So it clings rather than falling away. It works into seals. It films over camera lenses. It settles across solar panels in a fine, stubborn layer that never fully lifts. Apollo astronauts met a lunar cousin of this dust decades ago, and it worked into suit joints, scratched visors, and irritated throats after only a few hours of exposure. That was dust, with no perchlorate riding along inside it. Airlocks fight back. Electrostatic precipitators, air showers, suit ports that leave a contaminated suit sealed outside the pressurized shell entirely. Every trick engineers know goes into keeping the dust on the far side of the door. None of it is perfect. Every walk outside, every airlock cycle, every rover returning from a survey brings a little of the surface in with it. However careful the crew. Over months, then years, it settles on surfaces, circulates through the air system, and coats equipment nobody thought needed shielding. Breathe it in, and the danger compounds rather than fades. Perchlorate reaches lung tissue directly, no digestive system to slow it down first. Iron oxide compounds in the dust may generate reactive molecules that damage that tissue further on contact. Chronic exposure researchers suggest with real caution resembles the silicosis that has scarred the lungs of miners and industrial workers for over a century. A chemical burden layered on top of a mechanical one. But a miner leaves the shaft at the end of a shift. The exposure has an edge to it, a boundary, a place where it stops for the night. On Mars, there is no shift to clock out from and no shaft to walk out of. The dust is everywhere the settlement is, replenished endlessly by wind that never stops moving across the surface, and the entire planet is the source. That same dust does not stay content in the seals and on the panels either. Lift enough of it, spread it far enough across the sky, and it still has one more way to reach in and switch something off. Not a film on a lens or a grit worked into a seal this time. A planet-sized event, capable of blacking out a settlement's power for months at a stretch. Roughly every 3 to 4 Mars years, something close to once every 6 or 7 years on Earth's calendar, smaller regional storms feed on each other and merge, until dust wraps the entire globe in a single, continuous storm system. Astronomers have watched versions of this same event through telescopes for well over a century. It is not a freak occurrence. It is scheduled weather, arriving late but arriving reliably, and lasting anywhere from a few weeks to several months once it does. Picture that storm and the instinct is to imagine violence, sand scouring metal, panels torn loose, walls groaning under load, something closer to a hurricane than a breeze. That instinct is wrong and worth correcting directly. Mars's atmosphere is so thin that even a gust moving at 200 kilometers an hour carries roughly the same dynamic pressure as a gentle breeze back on Earth. There simply is not enough air here to hit anything hard. Not wind damage, opacity. The real danger is what the storm does to the sky, not to a wall. A global storm lofts billions of tons of fine particulate into the atmosphere. A pall thick enough that surface sunlight can fall by more than 90%. The sky dims for weeks on end. Day and night begin to blur into each other as suspended dust absorbs and redistributes what little solar energy still filters down. The whole planet disappears under its own weather, and it stays that way for as long as the storm chooses to last. On June 10th, 2018, that difference between wind and opacity turned lethal. Opportunity, the rover that had already outlasted its own 90-day design life 60 times over, ran entirely on solar power. As the storm thickened overhead, its panels stopped generating enough electricity to keep the critical electronics warm through the Martian night. Opportunity sent one last transmission and went quiet. Engineers kept listening for months after the skies finally cleared. Nothing answered. Not a boulder in its path. Not a mechanical failure. Not 15 years of wear finally catching up with it. Weather killed it, and weather did it simply by closing the curtains. A rover that had beaten its own warranty by a factor of 60, undone by an ordinary, recurring, entirely predictable feature of the Martian year, its power supply switched off, while the cold finished the rest. For a robot, that ending is a footnote in a mission log. For a settlement built on the same logic, panels feeding batteries, feeding life support, the identical storm becomes a slow-motion emergency stretched across months, rather than a single afternoon. There would be no single dramatic failure to point to afterward. No blowout, no breach, just a slow suffocation. Reserves draining a little further each day while one system after another gets switched off to conserve the watts that are left. Power generation collapses toward a fraction of baseline. Air processing, water recycling, heating, lighting, all of it has to draw down stored reserves or shut off, system by system, to keep the essentials alive. Nobody can say in advance how long any given storm will run. Some clear within a few weeks. Others have persisted past 3 months. And there is no way to know which kind is coming until it already has. We don't know in advance which storm a settlement will face. A colony has to be engineered to survive the longest one on record, not the average one, because averages do not keep anyone breathing through the third month of darkness. Surviving that means one of two paths, and both are expensive in the currency that matters most out here: mass. Battery banks large enough to hold months of full consumption in reserve, hauled across tens of millions of kilometers before a single panel is even unfolded. Or a power source that does not care whether the sky has gone dark at all: nuclear fission. NASA has already tested the concept. The Kilopower project ran a small fission reactor, a uranium-235 core paired with a Stirling engine to turn heat into electricity, producing about 1 kilowatt, with a design path toward 10. A functioning settlement would need many multiples of that, reactors totaling somewhere in the tens to hundreds of kilowatts, running continuously, indifferent to storms, indifferent to the sun's position, indifferent to how thick the dust has grown overhead. That solves the storm problem. It does not solve the deeper one. Every reactor is heavy cargo on a mission, where every kilogram is already fought over, mass that could have carried food, tools, or spare parts instead. Every reactor demands careful siting for heat and radiation safety, then years of unattended operation with no technician able to fly out and fix a failed pump or a cracked line. And leaning on fission alone simply trades one single point of failure for another. If the reactor goes down while the sky is still too thick for solar to help, the settlement faces the identical crisis it was built to avoid, only arriving from the opposite direction, the sun blocked overhead and the backup silent underground at the same time. The storm does not care which system gives out first. It only cares that for months at a stretch, one of them will. Power was only the first appetite the surface refuses to satisfy for free. Water and food were waiting on the same list. Assume, for a moment, that the power holds. The reactors run clean through the worst storm season. The battery banks never dip below reserve. The lights stay on through every dark month. What does all of that hard-won electricity actually buy a person standing on Mars? Two things, in the end: water and food. And even here, where the news finally sounds good, the ease is a mirage. Mars has water. That much is confirmed beyond argument. Orbital radar has mapped enormous stores of subsurface ice threaded through the mid-latitudes. Ice that has likely sat frozen in place for millions of years. The polar caps hold still more, buried under a seasonal skin of frozen carbon dioxide that grows and retreats with the Martian year. The Phoenix lander did not have to infer any of this from a distance. It touched down at a high northern latitude in 2008 and found water ice sitting only centimeters beneath the dirt under its own footpads. Problem solved then. Except confirmed is not the same word as accessible, not remotely. The ice sits locked in ground far below freezing. Reaching it means breaking that frozen regolith apart with equipment built to survive the cold that is breaking it, hauling the broken material to a processing site, melting it with heat. The settlement has to generate on its own, and then filtering what melts to strip out the perchlorate and dissolved salts before anyone drinks it, waters a crop with it, or feeds it into a machine that splits it into something more useful. Mining draws power. Transport draws power. Melting draws heat that has to come from somewhere. And on a world already rationing every watt, somewhere always has a cost attached. Purification draws filtration, and often chemical treatment on top of that. Electrolysis, the process that breaks water apart into breathable oxygen and usable hydrogen, pulls a serious jolt of electricity all its own, and a settlement of any size needs both gases running constantly, not once. None of these steps is optional, and none of them is free. Water on Mars is not a tap you turn on. It is a continuous industrial mining operation, run year after year, inside an environment that spends every hour it can at trying to freeze, corrode, or bury the very equipment doing the mining. Food closes the loop from the other side. Even with clean water on hand and perchlorate scrubbed out through hydroponic trays instead of native soil, the numbers stay stubborn. Mars's thin atmosphere transmits only a fraction of the sunlight a greenhouse needs, and that is the good case. A clear sky with no storm overhead. Powered lamps have to make up the difference, because the sky itself cannot be trusted to show up on schedule. Keeping a growing space warm enough for a living plant, against cold that never really lets up, means heating that runs without pause, the same steady draw a furnace makes, trying to hold an unheated barn above, freezing through a winter, with no spring on the far side of it. One genuine gift survives in all this. Mars's atmosphere is almost pure carbon dioxide, and a plant wants carbon dioxide more than almost anything else it is given. That part comes free. Nearly everything standing around it, the water, the nutrients, the light, the heat, has to be built, mined, or manufactured, and paid for in power that was already spoken for twice over. This is where the arithmetic turns dangerous. Every one of these systems leans on every other one. A power failure does not dim a single light. It cuts light, heat, and water pumps in the same instant, because all three draw from the same reactor. A dust storm that starves the panels does not just darken the sky overhead. It starves the greenhouse lamps, which starves the crop, which starves the people the crop was grown to feed. A breakdown in the water processor does not stay contained to what comes out of a faucet. It stops irrigation, and a stopped irrigation line kills a growing cycle as surely as a severed wire kills a light. These failures do not sit side by side as separate risks. They sit end to end, links in a single chain, and Mars offers nothing outside that chain to catch what falls when any one link gives. No river runs nearby to fall back on while a pump gets repaired. No wild crop survives beyond the dome to buy a season of slack. No spare reserve of breathable air sits waiting the way it might on a world built to hold one. On Earth, a broken well means a trip to a neighbor's tap, or a truck, or a reservoir a few kilometers off. On Mars, there is no neighbor, no truck route, and no reservoir that was not built and filled by the same hands running everything else. Every margin a settlement will ever have has to be manufactured by hand, hauled across tens of millions of kilometers, and maintained without a single visit from anyone back home, because the planet itself will not spare even 1 square meter of buffer. That is the price attached to everything a settlement can build. What waits next is a hazard nobody can build their way around at all. Gravity is not a hazard you can seal a door against. It cannot be filtered, mined around, or shielded off. It is simply the pull of the planet itself, quietly acting on every cell of a body for every hour of every day. And on Mars, the pull happens to be weak. Mars pulls at about 3.7 meters per second squared, a measure of how hard a world drags you toward its center, which works out to roughly 38% of Earth's pull. A person who weighs 150 pounds at home would weigh a little under 60 pounds standing on Martian ground. That is far more loading than the near weightlessness astronauts feel aboard the International Space Station. Bones and muscle need resistance to stay strong, some steady pull working against them, and 38% is at least a pull, not nothing. It is reasonable to hope that is enough. Hope is not data, and the data does not exist. Everything doctors currently know about the body and reduced gravity comes from microgravity, the near total weightlessness of orbit, not from anything close to Mars's partial pull. In that environment, astronauts lose 1 to 2% of their bone density every month, concentrated in the load-bearing bones of the pelvis and the femur. The kind of loss an elderly patient confined to strict bed rest might see in a year, repeating month after month with no floor in sight. Muscle wastes. The heart and blood vessels weaken from having nothing left to push against. Fluid drift upward toward the head, raising pressure behind the eyes and blurring vision. The immune system stops behaving the way it should. daily exercise, hours of it, slows this down across a 6 to 12 month mission. It does not stop it, and missions that run longer show the decline continuing anyway. Astronauts who come home eventually rebuild much of what they lost, walking again on a world their bodies still remember. Mars offers no such homecoming. A settler who loses bone density on Mars stays on Mars, under the same weak pull that caused the loss in the first place, for the rest of a life spent there. Whether 38% changes, any of this is unknown. Not partly unknown, completely unknown. No human being has ever lived in sustained partial gravity, not for a week, not for a day, and no laboratory on Earth can fake it. Lying tilted head down in a hospital bed shifts fluid the way space does, but it does nothing to remove the load from your bones. A parabolic flight buys a few seconds of Martian pull before the plane has to level out. Neither one tells you what happens after a year, or 5, or a lifetime spent standing on it. What happens to a skeleton built for 1 gravity after a decade under a third of it? Nobody can answer that today, because answering it means living it first. There is only one way to find out, and it is not an experiment anyone can run first and read the results of later. It is to put people on Mars for years and watch what their bodies do. The first residents are not settlers in the ordinary sense. They are the trial. There is no control group. There is no way to stop halfway through if the numbers start turning the wrong way. And if 38% turns out to be too little, there is no fix waiting. You cannot dial up a planet's gravity. Spinning habitats, rotating structures built to fling loose mass outward and fake the pull of a larger world exist on paper and could, in theory, add the missing loading back in. But building and maintaining a rotating structure on a planetary surface means building something close to a space station, only anchored to rock instead of orbit, which quietly defeats much of the point of having a planet to stand on in the first place. Every plan for settling Mars assumes the planet supplies enough gravity to keep a human body working. Nobody has confirmed that assumption. Nobody may confirm it for decades, not until people have lived there long enough to find out whether their own skeletons are dissolving under them. And building the spinning fix, if it is ever attempted, means solving an entirely separate set of engineering problems, bearings that never wear out, a structure balanced well enough not to shake itself apart, decades of maintenance on a machine that must never stop turning, layered on top of every other burden a Martian settlement already carries. Reproduction sits behind all of it, and it is the deepest unknown in the whole set. A colony that lasts has to raise children, and pregnancy, fetal growth, infancy, and the slow architecture of a growing skeleton are gravity-dependent processes shaped by 4 billion years of evolution, longer than complex life has crawled, swum, or walked anywhere on Earth, every bit of it tuned to one particular pull. Animal studies in microgravity have already turned up developmental abnormalities, altered gene expression, embryos that do not survive. Whether 38% avoids any of that is not known. Whether a child conceived and raised on Mars would grow a normal skeleton, keep a healthy heart, and go on to have children of their own has no answer today, and will have none until it actually happens to somebody. This is not a problem more funding fixes, not a problem better engineering fixes. If the human body needs more than 38% of Earth's pull to develop and reproduce normally, Mars stays closed to permanent settlement no matter how advanced the habitat wrapped around it becomes. Radiation was one number the planet refused to negotiate. Gravity is the second. It is fixed, a property of the world itself, as fixed as the distance from Mars to the Sun, unchangeable in a century, unchangeable in 1,000 years. Every hazard so far could at least be built against. Pressure gets sealed in, radiation gets shielded, however imperfectly. Dust gets filtered out, water gets mined and melted and cleaned. Gravity asks nothing to be built. It simply is what it is. and it will still be exactly what it is long after the last habitat is finished and occupied. It is not the only number like that on this list. It will not be the last one counted. Line up every number counted so far, and something worse than any one of them appears. A Mars settlement has to hold a pressurized shell against near vacuum. Every wall a dam, every seam a possible failure. It has to heat that shell through nights that fall well below negative 100 degrees Celsius. It has to shield the people inside from radiation that never stops arriving, awake or asleep, indoors or out. It has to mine and melt water out of buried ice, then wash or bypass the soil laced with a compound that attacks the thyroid. It has to keep breathable air flowing from an atmosphere that is 95% carbon dioxide, grow food inside walls that nobody can step outside of, and keep the lights and the heaters and the water pumps running through storms that can blot out the sun for months at a time. And it has to do every one of these things at once, continuously, with hardware that never stops degrading, cold, radiation, dust, and constant swings in temperature wearing down every seal and every joint together, year after year, with no factory nearby to replace what wears out. None of these problems sits by itself. They lean on each other. Each one is a load-bearing wall in the same structure, and pulling out any single wall brings the rest of the building down with it. Fail the power, and the water stops. Fail the water, and the food stops. Fail the heat, and the seals begin to crack. Fail any one of them for long enough, and the failure spreads sideways into every other system sharing the same reactor, the same pipes, the same sealed air. There is no such thing on Mars as one system quietly failing, while the others carry on around it. Think about what a failure looks like on Earth instead. A power outage still leaves you air to breathe, and a temperature you can survive for hours or days while someone finds the fault. A wall can crack in a storm, and the outside air will not kill anyone standing near it. A pipe can break, and rain still falls somewhere. A river still runs. A neighbour still has a working tap down the road. Even a bad failure on Earth usually just means discomfort, an inconvenience with time built into it. Earth's atmosphere and its water cycle act as a buffer, absorbing failure long enough for people to respond to it before it turns into something worse. Mars offers no such buffer. Step outside any wall, in any direction, and the environment is lethal within minutes, sometimes within seconds, through more than one mechanism at once. On Mars, a failure is not an inconvenience to manage. It is a countdown. None of this makes Mars impossible to visit. Robotic missions have already proven the opposite, again and again. A short crewed mission, perhaps 18 months on the surface, arriving with supplies already waiting, and a reliable line back to Earth, sits within reach of engineering that already exists. Dangerous, expensive, historic, and achievable all at once. A real mission worth planning for. But a mission is not a settlement. Communities that grow, raise children, and keep running for generations without resupply from Earth face something different in kind, not only in degree. Surviving a stay is one problem. Thriving for centuries is another. And the same hard limits keep showing up under every version of the plan, no matter how the habitats are arranged or how many redundant systems are bolted on. Radiation cannot be engineered away without shielding too heavy to land there. Gravity cannot be increased without building something that amounts to a space station bolted to the ground. The atmosphere cannot be thickened on any timeline a civilization could plan around. The soil stays toxic. Every breath of air and every drop of water has to be manufactured, at cost, indefinitely, by machines that are never permitted to stop, on a schedule that never has an off-season and never gets a day of rest. Mars is not a spare Earth, sitting in reserve, waiting to be switched on. It is an alien world, its air a poisonous trace, its ground soaked in radiation, its pull on the body still an open question after everything examined so far. It remains the nearest plausible place to land a human being. That was never in dispute. Getting there is faster, cheaper, and better understood than reaching anywhere else beyond Earth. But those are advantages of logistics, not of environment. Close is not the same as livable. Reachable is not the same as survivable for 1,000 years. Farther out, past the asteroid belt, past Jupiter, in orbit around Saturn, a different kind of world has been waiting. For decades it was dismissed outright. Too cold, too far, too strange to take seriously as anywhere a person could stand. A footnote in the search for a second home rather than a candidate for one. That dismissal belonged to an earlier generation of data. 20 years of new observation have quietly taken it apart. The reassessment reaches back farther than the word new suggests. It starts with a single spacecraft's camera, pointed at something nobody had managed to see clearly at all. In November 1980, Voyager 1 swept past the Saturn system and aimed its cameras at Titan, the largest of Saturn's moons, expecting to photograph a surface the way it had already photographed Jupiter's storms, Io's volcanoes, and Saturn's rings in exquisite detail. Those cameras had already resolved the churn of an alien atmosphere, active volcanoes throwing material into space, ice cracked into moving plates. Titan should have been an easier target than any of that. It saw nothing. A uniform orange haze wrapped the entire moon, and every wavelength of light Voyager carried failed to punch through it. Not a landscape, not even the outline of one. Just haze. An entire world reduced to a single flat colour, as featureless as a marble hanging in the dark. That failure to see was the first sign Titan was nothing like the dozens of other moons already catalogued in the outer solar system. Every other moon Voyager had photographed gave something up on the first pass. A crater field, a fracture line, a plume caught mid-eruption. Titan gave up nothing at all. A blank photograph could have meant a bad angle, a bad filter, a camera caught at the wrong moment. It meant something else. It meant an atmosphere thick enough to scatter light itself, thick enough to carry weather, thick enough to hide an entire world's geography from orbit. Ganymede carries a trace of oxygen so thin it barely counts as an atmosphere at all. Europa's is thinner still, a whisper escaping into space almost as fast as it forms. Titan's was not a whisper. Nothing else orbiting any planet in the solar system came close. Voyager's instruments went to work on what was actually up there, reading the light passing through the haze the way a chemist reads a flame. The answer arrived as close to reassuring as this list of worlds ever gets. Titan's atmosphere is roughly 95% molecular nitrogen, the same gas that makes up 78% of the air filling your lungs right now. The rest is mostly methane, with traces of hydrogen, ethane, acetylene, and hydrogen cyanide, a compound lethal in concentrated form, drifting through a chemistry that, by every reasonable expectation, had no business surviving on a frozen moon nearly 10 times farther from the sun than Earth. Out at that distance, sunlight arrives weak and cold, barely strong enough to drive the kind of chemical reactions that were now showing up in Voyager's readings. And yet there they were, an active atmospheric chemistry running on a world that should have been chemically frozen solid. But composition was not the number that changed everything. Pressure was. Voyager's radio signal, threaded through the haze on its way back to Earth, bent and slowed in a way that let scientists calculate exactly how much atmosphere was pressing down at the surface. The number came back at roughly 147 kilopascals, 1.45 times Earth's own sea level pressure. Denser than the air pressing on your shoulders as you read this. Not a trace of gas, not a thin exosphere clinging to ice. A wall of air heavier than the one over your own head, sitting on a moon in the outer solar system. Only one other body in the solar system carries anything close to that kind of pressure, and it is the worst possible comparison. Venus's atmosphere, nearly pure carbon dioxide, reaches roughly 9,300 kilopascals at the surface, over 90 times Earth's, under a temperature near 460 degrees Celsius, hot enough to melt lead sitting out in the open. Nothing about Venus belongs in any conversation about a place a person could stand. Titan's number sits in an entirely different category, higher than Earth's, but only slightly. Survivable, not lethal. Every other surface examined so far in this comparison has been a place the human body cannot last unprotected for more than a matter of seconds. Titan is the exception. Stand on its surface, and your body would not be fighting a vacuum trying to pull it apart from the inside. Your blood would not boil. Your lungs would not rupture, straining against nothing outside them. You would still need warmth. Titan's surface runs brutally cold, and you would still need your own air to breathe, since the nitrogen around you carries no oxygen your body could use. But you would not need a pressure suit. Not the rigid, joint-locked armor built to keep a body from bursting into vacuum. Just insulation and a mask. The atmosphere itself would press against your skin, the way air is supposed to. The way it presses against you standing in a room right now. Maybe a little more firmly than that. Of everything examined across two worlds, it is a single quiet mercy. A planetary surface where the air understands the shape of a human body instead of trying to erase it. That mercy came with a catch Voyager could never resolve. The pressure, the nitrogen, the whole strange chemistry above the clouds, all of it was known before anyone had seen a single rock, a single dune, a single drop of liquid on the ground beneath the haze. Every number in this section came from instruments reading light and radio waves through an orange curtain that never once parted for a camera. For 25 years after that first blank photograph, Titan's actual surface stayed exactly what it had always been, unseen. A world with an atmosphere the body could trust, hiding a ground nobody had ever laid eyes on. For 25 years, the haze kept it secret. Ground telescopes tried to peer through it, catching only faint suggestions of continents and dark regions floating beneath the orange. Hubble tried too, and came back with the same vague shapes. A hint of geography is not a landscape. Real understanding demanded a mission willing to go down through the clouds instead of squinting at them from orbit. And in October 1997, that mission left Earth. Cassini and Huygens traveled together, a joint venture between NASA, the European Space Agency, and the Italian Space Agency, built to do what Voyager's cameras never managed. The same 7-year cruise that carried Voyager's own instruments toward the outer solar system carried this one too, bending past Venus twice, then Earth, then Jupiter, borrowing velocity at each stop the way every mission bound for Saturn eventually has to. Cassini reached Saturn in July 2004 and, unlike Voyager, did not simply fly past and leave. It stayed for 13 years, crossing paths with Titan more than 100 times, aiming radar through the haze the way Voyager's cameras never could, slowly assembling a map of a moon nobody had actually seen. Cassini was only half the plan. Huygens, the probe riding along beside it, had one job and one chance to do it. Built by the European Space Agency, it separated from Cassini in December 2004 and began falling toward the surface on January 14th, 2005. A probe not much larger than a washing machine, entering the atmosphere of a moon more than 1 billion kilometers from the hands that built it. Entry came first, and entry was violent. Huygens hit the outer atmosphere at roughly 1,270 kilometers up, moving at about 6 kilometers every second. Friction against that thickening air heated the shock layer past 12,000 degrees Celsius, more than twice the temperature of the sun's own visible surface, for a few seconds that either destroyed the probe or did not. It did not. The main parachute opened, the violence stopped, and Huygens spent the next 2 hours and 27 minutes falling gently through Titan's sky, the longest descent through any atmosphere ever attempted anywhere in the solar system. 6 instrument packages recorded everything on the way down: composition, temperature, pressure, wind, and sound, relaying each measurement up to Cassini and back across that same billion kilometers to Earth. Then it landed and kept transmitting from the ground for about 72 minutes before its batteries finally gave out. What it found in that short window rewrote the conversation about this moon completely. High above the surface, Titan's atmosphere runs an organic chemistry factory that never shuts off. Sunlight and charged particles from Saturn's own magnetic field tear nitrogen and methane apart and stitch the pieces back together into something more complicated. Hydrogen cyanide, acetonitrile, benzene, toluene, an entire catalogue of carbon-rich molecules drifting down onto the surface like a slow, ceaseless rain of snowflakes. Several 100 million kilograms of it falls every year, roughly the weight of the Empire State Building dropping out of the sky, not once, but every 12 months, building up in layers meters thick across the ages. On Earth, chemistry this complex almost always means biology did it. On Titan, sunlight and physics do it alone. Not a sign of biology. A factory running on starlight and cold gas. Huygens' cameras, cutting through the last of the haze, showed something disarmingly familiar. Bright highlands, cut by dark branching channels, draining downhill into darker plains, the unmistakable shape of river valleys, startlingly like Earth, glimpsed from a descending aircraft. Mars has channels too, but Mars's are ancient, dry, fossils of water that stopped moving billions of years ago. Titans are not fossils, not dead, running right now. They follow the same mathematical rules real rivers follow on Earth, and the ground Huygens landed on still looked wet. Rounded pebbles of water ice, 10 to 15 centimeters across, sat scattered across a flat plain, the way stones settle in a riverbed after the water recedes. A probe pressed gently into the surface and found a thin crust over something softer underneath. And the moment Huygens touched down, its own instruments caught a spike of methane gas, its landing heat boiling a trace of liquid straight out of the ground it had just touched. Here, at nearly 180 degrees below 0 Celsius, cold enough to sit only a few dozen degrees above the point where nitrogen itself turns to liquid. Water ice is not a liquid at all. It's bedrock, as rigid as granite. But methane, a gas on Earth, is a liquid here. It evaporates, rises, gathers into clouds, falls as rain, and carves its way across the ground the same way water does on Earth, just running on a different molecule at a different temperature. Titan has weather. Titan has seasons. Somewhere on Titan, right now, it is probably raining. Cassini's 13 years of radar filled in the rest. Around the equator, wind piles dark organic sand into dune fields, stretching hundreds of kilometers, driven by an atmosphere half again as dense as Earth's own, thick enough to push sand the way Mars's thin air never could. Farther from the equator, rugged mountains and canyons of water ice rise into view, some of them cryovolcanic, cracked open by an interior warmed not by molten rock, but by the steady tidal squeeze of Saturn's gravity, erupting water and ammonia instead of lava. Ice volcanism, in other words. The same basic mechanics as a volcano on Earth, just running on frozen water instead of melted stone. And at the poles, the radar found seas. Kraken Mare, the largest, spreads across roughly 400,000 square kilometers, an area comparable to the entire Caspian Sea. Ligeia Mare, smaller at 126,000 square kilometers, still runs deep enough in places, over 160 meters, to swallow buildings dozens of stories tall without a ripple ever reaching the surface. Pungamad sits nearby, one more entry among dozens of smaller lakes, filling the northern lowlands. Cassini watched clouds gather over these seas, watched them darken, and watch methane rain fall from them. It caught sunlight glinting directly off open liquid. Unmistakable proof these were not dry basins, but real seas under an open sky. On one pass, something briefly lit up inside Ligeia Mare, held for a few orbits, then vanished. Maybe rising bubbles of nitrogen, maybe stirred solids catching the light differently. Nobody is certain yet. Mars once had water, long ago and long gone. Europa and Enceladus may hold oceans sealed away under miles of ice, hidden and untouchable. Titan is the only other world in the solar system with liquid sitting in the open right now, evaporating, raining, flowing, filling basins big enough to sail across. A moon voyager could not even photograph had turned out to be the most Earth-like place beyond Earth itself. What remained was the harder question, whether any of that natural architecture actually made the place somewhere a person could return from. It is a beautiful world. The deeper surprise sits underneath the beauty, in how much of Mars's cruelty this same natural architecture quietly undoes. Radiation is the place to see it first, because Mars never solved it. Titan's air is nitrogen stacked 1.5 times deeper than Earth's own, and that column does something no wall of aluminum or meter of Martian regolith ever managed. It stops cosmic rays before they reach the ground, the way Earth's atmosphere stops them, passively, permanently, without an engineer ever laying a hand on it. Titan also spends most of each 16-day orbit tucked inside Saturn's own magnetic field, shielded a second time before the atmosphere even gets involved. And when it briefly drifts back out into open solar wind, the thick air alone covers the gap. Added together, and the dose reaching the surface is estimated at next to nothing, potentially no worse than the background radiation Earth's own surface receives every year. Not a smaller version of Mars's problem. A different category of problem, solved instead of merely reduced. A child raised under Titan's sky inherits a radiation budget no worse than a child raised on Earth. A child raised on Mars inherits measurable cellular damage before its first birthday. The same air rewrites the other rule that has haunted this entire argument, the rule about walls. On Mars, every habitat wall holds roughly 10,000 kilograms of outward force, pressing against every single square meter, about the weight of 6 or 7 parked cars, stacked on a patch of wall the size of a kitchen table, all day, every day, for as long as anyone lives there, because the inside carries breathable pressure and the outside carries almost none. That is the balloon problem. A structure permanently trying to burst outward, one fatigue crack or one micrometeorite strike away from catastrophe. Titan's atmosphere presses down on a habitat, not up against it, harder than Earth's own air does. A Titan structure can run at slightly less than the pressure outside its walls, and let the atmosphere do the holding. The walls sit in compression instead of tension, pushed rather than pulled. A crack does not blow outward and empty the room in seconds. It lets cold air seep in slowly, an inconvenience with time attached to it, rather than a death sentence measured in minutes. The atmosphere that looked like the enemy on every previous world in this story turns out, on Titan, to be an ally. That difference compounds. Every settlement eventually breaks something. A seal, a joint, a system nobody predicted would fail in exactly that way. On Mars, a broken seal is a countdown. On Titan, it is a maintenance ticket. Centuries of operation mean thousands of small failures. And a world that turns failure into repair time instead of into a body count is a world built to actually last. Then there is what the ground itself offers. And here the contrast with Mars is almost unfair. Mars's soil had to be avoided, sealed out, kept off every surface that mattered. A contaminant standing where a resource should have been. Titan's surface is the resource. Its lakes and its damp high-latitude ground hold liquid methane and ethane in quantities that make the idea of running out almost meaningless. Burn that fuel with oxygen and it gives back heat, water, and carbon dioxide, 3 things a settlement needs every day. The oxygen has to be made, but it can be made from the crust itself, water ice, mined and melted and split apart by electricity into oxygen for burning and breathing, and hydrogen left over as a raw material. Nitrogen, the gas that fills nearly the whole sky, is already sitting there for the taking. And on Earth, nitrogen combined with hydrogen through the same reaction that manufactures fertilizer, the Haber process, becomes the ammonia that feeds crops. Titan can run that same chemistry without ever importing a feedstock from Earth. Even the dune fields carry raw material, tholins, the brownish organic solids built from carbon, nitrogen, and hydrogen, a possible source of plastics and adhesives still being studied. Fuel is not something a Titan settlement manufactures from scratch. It is literally underfoot. What Mars forced engineers to build from nothing, Titan hands over as a planet-scale chemical infrastructure already assembled, waiting only to be tapped. There is more sitting beneath all of it, and here the honesty has to slow down. Cassini's tracking of Titan's own wobble, small shifts in its orbit measured with extraordinary precision, pointed to a global ocean of liquid water buried under 50 to 100 kilometers of ice, likely carrying dissolved ammonia to keep it from freezing solid, possibly touching a rocky core below. Nobody can reach it. Drilling through that much ice sits well beyond anything current technology can do, but its existence alone makes Titan one of the most closely watched targets in the search for life beyond Earth. An interface of rock, water, and organic chemistry running quietly in the dark. A question nobody can answer yet, and nobody should pretend to. The clearest picture of what all this natural architecture could mean for a person standing on Titan comes from a machine scheduled to land there before anyone does. In 2028, a spacecraft the size of a large automobile is set to launch for Saturn, arriving sometime in the mid-2030s. Dragonfly is a nuclear-powered rotorcraft. Its battery recharged between flights by heat from its own radioactive core rather than by sunlight it will rarely see. It flies because Titan lets it. The air is half again as dense as Earth's, and the pull holding it down is only about 14% of Earth's own. Light enough that a 150-pound person would weigh about 21 pounds, standing on that ground, lighter even than on Mars. Thick air and weak gravity together mean a rotor barely has to work to generate lift. Dragonfly's 8 rotors will hop roughly 8 kilometers at a time, land, recharge, and hop again, covering more than 170 kilometers over a mission expected to last about 2.5 years. Opportunity, dragging its wheels across Mars for nearly 15 years, covered barely 45 kilometers in all that time. Titan's atmosphere does not just protect a settlement and feed it, it turns the entire moon into navigable airspace, open to rotorcraft and airships in a way no wheeled machine on Mars will ever match. 14% gravity is the one number in this section that does not flatter Titan, weaker than Mars's own, untested in any human body for longer than a few seconds of freefall. That debt is real, and it does not disappear just because everything around it looks so favorable. What remains is a full ledger now. Radiation, pressure, failure tolerance, resources, gravity, every hazard that made Mars so difficult to settle quietly listed against its answer. What was still missing was placing that ledger side by side with Mars's own, line by line, and asking which world any of this actually favors once every number finally sits on the same page. Start with the air, because no other number in this comparison is more lopsided. Mars holds its atmosphere at roughly 600 pascals, almost entirely carbon dioxide, a pressure so thin it barely counts as air at all. It sits on paper more than it sits on the ground, unable to shield radiation, unable to carry a wing, unable to keep a body's fluids from boiling. Titan's atmosphere runs to about 147,000 pascals, built overwhelmingly from nitrogen, and it performs every service Mars's air cannot. It blocks cosmic radiation by sheer depth of column. It buffers temperature, it holds a rotor aloft, it removes the risk of a habitat failing outward in an instant. The gap between the two numbers works out to a factor of roughly 245. Mars keeps a trace. Titan keeps an ocean. Radiation follows the same shape, and it is the sharpest number on the whole ledger. Mars delivers roughly 233 millisieverts a year at the surface, climbing towards 7,000 over 3 decades unshielded, a dose no known architecture brings down to anything Earth would consider survivable long-term. Titan's dense nitrogen intercepts the same cosmic particles before they ever reach the ground, the identical physics that protects every person on Earth, and Saturn's magnetic field adds a second layer on top of it. The estimated dose at Titan's surface sits near nothing. Not a reduced hazard, a removed one. Gravity is the one place this ledger tips back toward Mars, and it deserves an honest hearing rather than a quiet dismissal. Mars holds its surface at 3.7 meters per second squared, about 38% of Earth's pull. Titan holds 1.35, about 14%. Neither number has ever been tested in a living human body for longer than the free-falling seconds of a parabolic flight. So the comparison is really a contest between two blind guesses, one of which happens to carry a larger number. Not a clear win, a guess with a bigger number attached. It is plausible that Mars's gravity supports a healthy skeleton across a lifetime, while Titan's does not. It is equally plausible that both fall short of whatever threshold the body actually needs, and both worlds end up requiring the same spinning, engineered workaround. Either way, nobody currently alive knows the answer, and pretending otherwise would be its own kind of dishonesty. Temperature looks, at first glance, like Titan's disqualifying flaw. Its surface holds near minus 179 degrees Celsius, a gap of roughly 200 degrees against a comfortable interior. Mars's average cold, near minus 60, opens a gap closer to half that, but cold, on its own, is a problem the 20th century already learned to solve. Liquefied natural gas terminals, aerospace fuel depots, storing liquid hydrogen, superconducting laboratories, all of them already hold temperature differences on this scale, routinely for decades without incident. Demanding? Yes. New physics? No. What actually separates the two worlds is not the size of the temperature gap. It is what happens when something breaks. A thermal failure on Titan is slow. Heat leaks out, the temperature drifts, someone notices the drop on a gauge and has hours, sometimes days, to find the leak and patch it. A pressure failure on Mars is not slow. Air rushes outward into near vacuum, and the room becomes unsurvivable within minutes. One failure gives you time, the other gives you a countdown. Multiply either failure by centuries of continuous operation, and the difference stops being a footnote. It becomes the whole story. The ground itself completes the picture. Mars offers a toxic, static charged dust that has to be kept out of every seal and every lung. Titan offers water ice for bedrock, hydrocarbons for fuel, nitrogen for fertilizer, raw material stacked instead of hazard buried. And on power, the case against Titan sounds strong until it is compared honestly. Sunlight arrives at Titan's surface at about 15 watts per square meter, roughly what a single dim reading lamp draws, spread across however much ground needs lighting, which makes solar power there close to useless. But Mars cannot run on sunlight alone either. Its own storms erase more than 90% of incoming light for weeks at a time, which is why nuclear power was never optional on Mars to begin with, only assumed. The difference is what sits behind the reactor. On Mars, if the reactor fails, there is no second system waiting. On Titan, the lakes themselves are a second power source, Methane and ethane burned with locally made oxygen, the same chemistry that heats homes across Earth every winter, in quantities that make running out almost a theoretical concern. None of this erases what is genuinely hard about Titan, and the honest ledger has to hold both sides at once. First, the trip itself takes 4 to 6 years each way, against Mars's 6 to 9 months, 5 to 8 times longer. With years of confinement and deep space radiation, the body was never built to absorb quietly. Second, a message takes over an hour each way to arrive, so Earth cannot run a Titan mission the way it runs a Mars one, and every crew has to carry the authority to decide things Earth would normally decide for them. Third, the cold demands cryogenic rated hardware throughout, seals, lubricants, metals that will not turn brittle and crack. Fourth, that weaker pull underfoot may prove worse for a body than Mars's stronger one, not better. Fifth, daylight on Titan's surface arrives dimmer than 1% of Earth's, a permanent amber twilight with no blue sky and no visible Saturn, demanding artificial light for every growing plant and every waking hour. Sixth, a Mars crew can go and come home within 2 or 3 years. A Titan crew cannot. A round trip runs past a decade, long enough that anyone who leaves for Titan is not really planning a visit. They are planning a life there. Seventh, a broken part on Mars can be resupplied within a season. On Titan, resupply takes years, which means nearly everything has to be repairable or replaceable from what the settlement already carries with it. That list is long, and none of it should be waved away. But look closely at what kind of problems it actually contains. Every one of them, distance, delay, cold, dim light, slow supply, sits inside physics already understood and engineering that can still improve. Not one of them breaks a law of nature. Mars's 2 worst numbers do. No spacecraft, no shielding, no clever material yet imagined, brings galactic cosmic rays down to something a body can absorb across a lifetime, and no engineering project changes how much mass a planet carries, which means no engineering project changes how hard Mars pulls on a human skeleton. You cannot add an ocean of atmosphere to Mars on any time scale shorter than geological. You cannot add mass to a planet to make it hold a person's bones together properly. Titan's hardest problems shrink as engineering matures. Mars's hardest problems do not shrink at all. They sit there, fixed, exactly as difficult in 1,000 years as they are today. None of this argues for abandoning Mars. People will likely stand on its red ground within 2 decades, and it will earn its place as a research outpost in the same spirit Antarctica has. A hard, worthwhile place to work, not necessarily a place to raise a family for 10 generations. What the comparison actually argues against is treating Mars as the only serious answer, a habit built from proximity and momentum, rather than from ever placing its numbers next to anyone else's. Set side by side with Titan, Mars wins on distance, on familiarity, on how soon a flag can be planted. Titan wins on nearly everything that decides whether people are still there centuries later. Air that shields instead of merely existing. Cold that can be engineered around instead of radiation that cannot. Chemistry that feeds a settlement instead of poisoning it. Which world is better depends entirely on what is actually being asked. Speed favors Mars, endurance favors Titan, and somewhere beyond Saturn's rings, that patient, nitrogen-wrapped moon keeps orbiting anyway, its lakes of liquid fuel catching a light too faint to cast a shadow, its atmosphere quietly solving, for free, problems Mars has never been able to solve at any price. It has been doing this for 4.5 billion years without anyone watching. The only real question left is whether we are curious enough and patient enough to look past the nearest world and ask whether the harder journey leads somewhere better to live.